All right. So let's start. So yeah, thanks for being here, first of all. Let's see if I can make it full screen. Do you see it? View, full screen mode. So the presentation took me some time to prepare it, and unfortunately I didn't manage to rehearse. So probably it will be a bit sloppy, so pardon me for that. All right. So the problem is how to derive lower bounds for Bayesian regret minimization.
There's
Spheros. Yeah,
just to
let's do like this. This is actually a problem that people have not studied that much. There are just a couple of papers that have been published very recently where they study Bayesian regret. And I think it's an interesting problem. Most people, they study frequentist regret. It's not clear to me what is the right notion to use. And so I hope this presentation can give some details and maybe spark your curiosity. So, okay. So this is the overview, very, very succinct. All right. So the paper that I think started all of this is this paper from Lai that you can also see on the top right here. A very, very strong guy, in my opinion. And this paper is from 1987. It's a follow-up of another paper on bandit models from 85, another very famous paper that basically started the entire field. Lai introduces the UCB algorithm, introduced the idea of using optimism. He derived instance-dependent regret lower bounds. So this guy really managed to do a lot of things. He's really one of the founders of this field, I think. Unfortunately, passed away recently. He was at Stanford, I believe. Um, but yeah, he gave multiple contributions also in the field of change point detection and so on. So this is a follow-up of the 85 paper. The 85 paper is about frequentist regret. And in this paper, instead, he studies the Bayesian regret. They use different terminology at the time, but it's about Bayesian regret. We will focus on unstructured multi-arm bandit problems. So we don't assume structure underlying the problem. There are some papers recently, like this paper from Atsi Daku, 2023, where they study Bayesian regret. But overall, there are not many papers. So we will go into the details of how to derive the lower bound for this case, and then maybe discuss some extensions and considerations. So we begin by describing what is the model. We have a classical multi-arm bandit problems with k arms. In each round, the learner chooses an action, AT, and receives a reward, RT, sampled from some distribution parameterized by theta. So each arm is characterized by some density function parameterized by theta with respect to the Lebesgue measure. And we assume that theta is a parameter unknown that belongs to some open set theta that is a scalar, the theta. And we also indicate by mu a theta the actual mean value of the reward of arm A. Basically, it's this expectation of the rewards over that is essentially an integral of the reward given this density. We also have the Bayesian prior. We assume that we have independent priors, but this is not needed. Actually, we can have also priors that depend in some way on each other. Actually, Lai in his paper, it derives the general lower bound Here we make this simplification just for the presentation. And then we indicate by mu star theta the maximum value of reward, of the average reward. So the average value of the best arm. Yeah, and very importantly, theta, it's the parameter of the model, so theta kind of represents the model. So in Bayesian analysis, we model the model. So in this case, theta is a random variable too. This is different from the frequencies case, where in the frequencies case, you assume that there is an underlying parameter that is fixed that you want to somehow estimate and work with that. But in Bayesian analysis, you need to model the underlying parameter also as a random variable.
So one thing like that.
Yeah.
So the definition of mu A is like the expectation of the absolute value. Is that
No, I mean it's without absolute value. What I wanted to say is that
it's integral.
yeah, it's integral. So the density F needs to behave nicely. Yeah, that's a type. Yes, so we studied just regret minimization where we have a fixed horizon T, but we could also study this for best arm identification, but this is another topic. And just to maybe spark your curiosity here, here actually we have 3 different plots. In each plot, we have different priors, uniform, Gaussian, and Bernoulli. And for each plot, I try to sample bandit problems with 5 arms from the prior. And then for each problem, I compute the frequency's lower bound. And then I average over all the sampled problems. So what you see in blue is this average frequency's lower bound. And the shaded area is actually the confidence interval that you get. So what is going on here? So what is going on is that we cannot simply apply the frequency's lower bound and average. It will not work. It simply doesn't work because the assumptions that we use to derive the frequency's lower bound don't hold in the Bayesian case. And we will see why is that. The fundamental idea is that in the Bayesian case, the gap between the best arm and the second best arm can be vanishingly small. It can, in the limit, it can be 0. The frequencies case is not able to deal with this case. The frequencies assumes that in the limit we sample at some rate, but this rate is not uniform over the parameters theta. So there is this important notion of uniform convergence that we need in the Bayesian case. That in the frequencies case is not assumed. In the frequencies case, you have pointwise convergence. For a given model, you have this convergence rate, but this convergence rate doesn't need to be the same across all the possible thetas. But for the Bernoulli priors, where each arm can have average reward 0 or 1, we don't have such problem. The gap cannot be as small as you want. It will be always 1. So that's why we don't observe this in the Bernoulli case. And in the orange, you see the actual true lower bound for the Bayesian regret. And yeah, I computed the lower bound for the frequencies using 3 million samples. So that gives you an idea
there
of.
it gets inverted now, somehow, in the Bernoulli case.
Yeah, but the confidence interval in the other 2 cases is so high that you cannot really tell where is the true frequencies lower bound. It doesn't matter how many samples you get, it's simply not well defined. Yeah.
1 over delta,
Yeah.
it's like small.
It simply doesn't exist. All right, so to be able to analyze the frequency's lower bound, we need to make some assumptions. We assume the density to belong to the single parameter exponential family, where the density then is given by this formula. So exponential of the parameter theta a times r minus the cumulant generating function. And the cumulant is defined as the logarithm of the expected value of the exponential of the random variable. Theta is called the natural parameter. And here, this type of distribution can also represent Gaussians with known variance. When the variance is 1, theta is exactly equal to the average value. So it's called the natural parameter. And we also have this function psi, and it's defined as the derivative of psi with respect to theta is equal to the average value. And we have that the second derivative of psi, so the second derivative of the cumulant is the variance. So in the Gaussian case, I said that theta is the average value. Psi dot is the average value. It's increasing theta. In the Gaussian case, it is. But in general, it's always increasing for single parameter exponential families. And we denote by theta star the maximum value of theta A. So in the Gaussian case, theta A is equal to mu A. So this is equal to the best mean reward. Another important property is that we can define the Kullback-Leibler divergence in this way. It's defined as the difference between two parameters, theta, theta prime, times the average reward of theta A, minus the difference of the cumulant between theta A and theta prime. And because of, actually, you can think of approximating this with Taylor, and you can see that all of this is actually equal to this integral here. So this is an integral between theta A and theta A prime that weights the second derivative of psi with t minus theta A. So you can think of this as the remainder of a Taylor expansion, actually. This property will be used during the presentation, so let's spend a bit more time on this. Psi second, so the second derivative of the cumulant, first of all, it's always positive, which means that, and we know this because psi dot is increasing theta A. We are considering an open set. So it's also, and this is a bounded set, it's not diverging. Psi second. So knowing that psi second is positive will be useful to lower bound or upper bound this integral. Also knowing that it's bounded, because then we can lower bound the integral by the minimum value of psi dot over this open set, or upper bound with the maximum value. And in the case of Gaussians, psi dot is equal to theta A, so psi second is equal to 1. So it's always equal to 1. Yeah.
So the psi dot theta A equals to mu A theta?
In the Gaussian case is equal to theta A. Yeah.
So what is mu A theta defined in other cases?
Yeah, I don't know now by heart. Like for Bernoulli, for exponential, for Poisson, it's defined in other ways. But yeah, it depends on the cumulant. So you derive it from the cumulant. What is the definition of psi and psi dot?
Yeah, I was wondering the definition of mu A.
Mu A, it's from the previous slide here. So mu A is simply the average reward without the absolute value.
Yeah, the Gaussian case, it agrees.
This is the density that we use.
In some cases, I see, yeah. In
But
Gaussian
yeah.
cases, mu A is like theta A.
Yeah.
In other cases, that may be different.
Yeah. So this is what I just told you. For the single parameter exponential distribution family, we have that these inequalities here. So the difference in mean values between psi dot y and psi dot x can be upper bounded, lower bounded this way. So we can go through the proof. It's very quick. So first of all, why do we need to look at this difference here? It's the difference between average values. This is the gap in bandit models. So it's very important to try to control this quantity. So by the mean value theorem, since this function is differentiable over an open set, we know that there is a point in this set such that this difference here is equal to the second derivative of psi evaluated in that point times y minus x. Y and x here are the natural parameter theta. And then we know that psi dot is positive. We can, the set is bounded. We can find the minimum value of psi dot z times y minus x. So this lower bounds the difference. So we have a psi second. This is related to the KL divergence from the integral representation. So we can upper bound the integral using the maximum value of psi dot here. And when you upper bound this with the maximum value of psi second, you are left with an integral t minus x, which is quadratic. So you get x minus y squared. So when you combine these two inequalities, so what we have is this difference is equal to this, but then since psi second is always positive and this is the maximum, sorry, this is not the maximum, but for sure it's smaller than this quantity here. In the end, we can lower bound all of this in this way. Yeah, this is a typo here. It's not x.
Wait, so when you get the
It is a minimum. It's this quantity here.
oh, because we have the okay, yeah, sorry, I didn't see that. Okay.
Could we go to the previous slide? It's looking for the. So when I look at this theta stuff, should I think about its condition on theta or it's
Yeah, this is for yeah, this is for like fixed data.
Maybe it's not a typo.
Sorry?
I think it uses, maybe it's not a typo. It uses that the second derivative is increasing, then that's probably true for the exponential families.
No, so psi dot is increasing, not psi second. So psi prime is increasing, not psi second. Psi second, we know that it's positive, but because of that, then psi prime is increasing. Strictly positive. So here it's it should be mine over z that belongs to AB, and then it appears at the numerator here. Yeah, and then we use also this property.
Okay, so you're using the first bit, and then the second one is like lower bound y minus x.
Yeah.
In terms of like the d.
Yeah.
Yeah.
All right. So this was just the introduction.
Okay.
So, all right.
So like we're going to use that inequality eventually.
Yeah. Yeah, eventually.
Just like just to see like again, just so we can admire it. So this is in the gaps. I guess the mean bounded by.
So the gap is lower bounded by the Kerr divergence of the parameters divided by the difference of the parameters. But you can also upper bound the gap by the difference of the parameters.
So the C is not going to matter by the variances.
No, the constant, they will not matter. And yeah.
Yeah.
All right, so regret minimization. We need to introduce what is an allocation or sampling rule. So we define the sampling rule of the learner to be a sequence of measurable functions, each of which associates past data with an arm. So we can think of like the arm that you select as like trying to compute something given the past data. So what is the past data? The past data is simply all the observation that you have collected, but then maybe you also have some randomization in your method. For example, in Thompson sampling, you try to estimate the posterior and then you sample from the posterior. The sampling process can be seen as having an additional uniform random variable. So sampling from a distribution can always be seen as basically sampling like from the inverse of the CDF using a uniform random variable. So when you evaluate the inverse of a CDF on a uniform random variable, this is equivalent to sampling from the CDF directly. So this is that's why we can always see sampling from some distribution as in reality sampling a uniform random variable, because then if you evaluate the inverse of the CDF on that uniform random variable, it's equivalent to having sampled from the CDF. So yeah, Thompson sampling, all the randomization methods can be seen essentially as measurable functions of past data and uniform random noise. This is something that people usually omit. And we assume this sequence to be IID, independent from everything else. And then finally, we let NAT to be the number of times you selected arm A up to time t. So let's start. What is the regret? For a fixed model, we can define the regret at time t as this difference here. So it's the sum over time between the best value of the arms and the mu AT. Mu AT is the average value of the arm you selected at time t. And here, this expected value over theta means that we have a fixed theta. It's like we have condition on theta, okay? I didn't want to put the condition because it looked very ugly. But this is the meaning of expectation theta. For a fixed theta, we can also write the first bit as t mu star minus the sum over A of mu A times the number of times we selected arm A up to time t. We use the fact that capital T can be written as sum of arms of NAT. So we get the gap times the number of times we selected arm A. So in the end, we get the usual regret definition over arms of the gaps times the number of times we selected that arm.
For the second equality, we will need a definition over the first term of x. So like
no, here theta is fixed. Like we don't need it. It's not a random variable yet.
The conditioning on a fixed.
yeah, but then for the first term, like t mu theta star theta, you also need like e theta outside, right?
No, not yet. This is like regret given theta.
Oh, I see. Oh, yeah.
Yeah.
No, it means that we have a fixed theta.
Oh, it's a condition. I see. Okay.
Yeah.
But now it's that. That's
The notational choice.
All right, and then if we treat theta as a random variable, then we just need to simply take the expectation over theta from the prior of this regret. This is the frequentist regret. So in the end, when we integrate over the prior, we get the Bayesian regret. So now, because of this integral is what will cause all the issues. But let's maybe try to think about what is the meaning of this Bayesian regret. Should we consider the model theta as fixed or not? Why should we average over the prior if the problem maybe is fixed in reality? Like, if you give me a problem, why should I think that it's random? Maybe it's probably fixed, no?
Is that they're proposed by that guy, right? That's base, right?
Yeah, that's base. Like, if we have some drugs that we need to test, and we want to verify the efficiency on some populations. Should we think that the populations have a fixed underlying parameter or not?
Right.
Or maybe when we go to the casino, and we want to play the slot machines or the bandits. Should we think that the machines have a fixed underlying parameter or not? To me, this is still not clear. But what's interesting is that in the field, people have applied Bayesian techniques like Thompson sampling to the frequencies regret, and it works. It works because, in my opinion, it's just a way to do epistemic exploration, to be able to reduce the confidence around the true parameter. It's a nice exploration. It incorporates the prior that you have.
I mean, I guess
Yeah.
like a setting where maybe like a Bayesian view makes a lot of sense. It's some meta learning like thing where like, the patient that will show up and you're going to like run some like full treatment on that person.
Yeah, but once the patient appears, it's like the problem is fixed. It's that patient. You will not
Yeah,
get
yeah.
another patient.
Right. Well, right. Let's say, yeah. Well, but let's say you are the government, like you have like a huge hospital, so there's not just one patient. Yeah, but I guess when the patient shows up, like
It's like a realization.
It's there, right?
Yeah, we shouldn't treat it as random anymore. Right. So overall, I still have I'm more frequentist, let's say. But I think it's important to also study this setting to understand. Maybe it will be useful in some way. So for me, it's still interesting to understand what's going on. So yeah, let's focus on the Bayesian regret. Yeah, another interesting thing is that actually this problem of regret minimization can be solved with dynamic programming, also in the Bayesian case. But the problem becomes impractical for very general multi-rank bandit problems when the horizon is large. But just to give you a simple example, let's say you have a Bernoulli bandits, so the rewards are Bernoulli, and the prior is uniform. You can easily derive that the posterior is a beta distribution. This beta distribution is only characterized by the number of times you chose that arm and the number of times you observed one. So you have only these two parameters. So you can define an MDP with these two parameters. So the state is this tuple for each arm, and then you can try to solve this MDP. So if you find the optimal policy for this MDP, essentially you're solving the Bayesian regret. You can use dynamic programming, and this is essentially the idea behind Gittin's policies to define an MDP with a certain state and try to solve it. But it's unscalable, but maybe I guess you can apply RL. Maybe it's also possible to do some in context learning, I guess.
Right.
But yeah, so it was unscalable at the time. Maybe now it is. Who knows? So let's go into the proof. And this will be a bit tough, I think.
Okay.
So proof idea, well, I already spoiled you that this will not work. So maybe the original idea is to just take the frequencies lower bound. So we take the limit and then we integrate. But this will not work because the limit is pointwise. It's not uniform. So probably you're not familiar with the frequencies lower bound technique, but to derive the lower bound, we need to assume that the policy, so the sampling rule, will sample suboptimal arms at a rate that is not exceeding the logarithmic rate. So you can show that optimal methods sample suboptimal arms at a logarithmic rate. So you impose the assumption that your sampling rule will not sample at a polynomial rate. But this is something that it's only pointwise. It's not uniform over models. So we cannot do this limit and then integrate. We need to integrate and then take the limit. And we need to have some sort of uniformity in theta. But let's, just for the sake of the argument, see what happens if we still try to do the frequentist analysis. So this is what I just told you by words. Sampling rule pi is uniformly fast convergent if for all models we have that in the limit we are sampling at a rate that is not polynomial. So it's like logarithmic. So this small o of theta of t alpha for all alpha 0, 1 means that you will not sample at this rate. You need to be much slower than polynomials. It's, for example, logarithmic. So this is another way, maybe this is a bit more general than say big O of log t. This could also imply log t. But by using this result and using a change of measure argument, we can show that an optimal method should sample at this rate, a suboptimal arm. So the number of times you sample an arm that is suboptimal should be logarithmic in t divided by the KL between theta a and theta star. But the condition is not uniform in theta. So the convergence is pointwise. The rate of convergence for different thetas is different. For a certain theta, you could have a certain speed of convergence. For another theta, another speed. If you want to have a uniform convergence, you need to guarantee for all theta a certain speed of convergence. But when the gap gets very small, you have that this speed explodes essentially. So, for example, if we suppose that theta star is actually equal to theta a plus epsilon, then this KL, like you can see that this is roughly epsilon squared. And when you let epsilon go to 0, it will just explode. So this is what happens. And we can also see it here, what happens, like what is this log t divided by the KL for different values of epsilon. So for a fixed epsilon, which is the frequentist case, in the frequentist case, the model is fixed. We get the blue curve. But for epsilon that has different rates, we get even like this curve or this one. So that's why it diverges. So we cannot just say this pointwise converges. We need some uniformity. So that's the reason why we cannot apply the frequentist technique. Now we will try to understand how to do it in the Bayesian with a uniform assumption.
But what happens, so if the epsilons are very small, are not in the prior, like that they're not likely, then it should kind of work, no? Because you effectively have some, let's say, same epsilon. Let's say that in the what's the name? Bernoulli case, you show where the gaps are always the same. And then should that strategy just kind of give you the right thing?
Yes, but yeah, there are some assumptions on the prior that I didn't write explicitly because it's a bit too technical otherwise. That basically prevents the Bernoulli case.
Okay.
So essentially, we have an open set of parameters. So in the Bernoulli case, you don't really have an open set. You have 0 or 1. And then you need to have some sort of uniform continuity on this open set on the prior.
So then kind of prevents these like gaps not going very small.
Yeah, in the Bernoulli case, yes. But if you have an open set of parameters and you have the prior that is uniformly continuous on this open set, then the case that the gaps will explode will always occur.
I see.
But in the Bernoulli case, we don't have that. It's a bit different. But I think it was still a nice example to show.
Yeah, no, just
You had questions? Okay. All right. So just a bit of notation.
Ichin is like a base regret fanatic. So
So we define theta minus a to be this vector where we remove arm a.
Yeah.
We also define the prior without HA. So it's the vector of priors without HA. we define theta minus a star to be the best element in theta minus a without arm A. Recall that psi dot is the mean value. It's increasing because psi second is positive. Theta star is the parameter of the best arm. So the first thing we do is to this sum over arms to replace this condition mu a theta smaller than mu star theta directly with the parameters of the models. So the proof idea is to try to uniformly lower bound the quantity that appears in the regret, gaps times n, over a small region around theta star. The reason why we do this is because the largest contribution to regret is the region where the gap is very small. So we try to look around the region where the gap is very small, because when the gap is very large, it will not contribute much to the regret. So we need to look around the small gap region. So this is what I wrote before. When we integrate this quantity, we get the integral here. We can write this sum as the sum over all the arms times an indicator. And then we can simply swap the integral and the sum. And so we get this integral over theta such that theta a is smaller than theta minus a star. So why is that? So here we have an indicator, theta a minus theta star. So theta a cannot be optimal. The optimal must be in theta minus a star. So when we bring this indicator into the limits of the integral, we can also write it as integral over theta such that theta a is smaller than theta minus a star. All
I
right.
didn't understand. So, okay, so we are going to integrate the regret over the thetas, blah, blah, blah. Then the first thing is just like you're rewriting the thing above. And then, okay, you're adding the indicator, which is the theta a is less than theta star.
Which means that the best arm must be different from A. So the best arm must belong to theta minus A.
Oh, I see. Right. Okay, yeah, now I understand.
Yeah.
It's a strict inequality or it's less than equal to?
Strict.
Yeah, it's just saying like, yeah. So the red thing means that A is not optimal.
Right.
So the definition of theta star A is like the optimal arm not including A. So A is not optimal. So it's actually just the optimal.
Right, that relax it's possible to be equal though. Since that A.
So that thing is theta star basically because like the first sum is when A is only activated when A is not optimal.
Right, that's true.
And then the theta star slash A is the optimal arm that is not A. But A is not optimal. So it is actually just the optimal arm.
So theta star and theta minus A star are equivalent on this set.
Yeah.
Because A is not optimal.
Yeah, I was confused initially because I thought somehow in my mind, like the theta star thing was something that was not A and not the optimal things. So the second, but no, this is just the optimal thing that is not A, which could be the optimal overall.
Are you still following?
Yeah.
All right, so let's focus on the integral because this sum over A, it doesn't really matter that much. So yeah, now we need some help from Professor Lai. So he had another paper, always from 87, where he noticed that with a single parameter, upper confidence bounds methods in this Bayesian case need to satisfy this very strange assumption. So if we denote by S this quantity, so the minimum time where the UCB will be like smaller than the true value plus some epsilon, then we must have that the probability of S being smaller than this quantity tends to 0 in the limit as capital T goes to infinity. What it means is that the infimum of this quantity must happen at the rate log n epsilon squared divided by the KL. In other words, you need to sample at this rate to detect an epsilon difference. This is really what this condition means. Yeah, sorry, this should be capital T, not capital N. So what this condition really means is that to notice an epsilon difference, you need to sample at this rate, log T epsilon squared divided by epsilon squared, where epsilon, yes, it's the difference that we defined here. And this condition is uniform in epsilon that belongs to this interval, where alpha T and beta T are quantities that satisfies these conditions. So if we try to integrate this quantity here over epsilon in this interval here, what we get is essentially something that is log T epsilon squared divided by epsilon plus a constant. Here I didn't really define the limits of the integral, so we still see the epsilon. But the idea is that this quantity will appear in the regret lower bound. So if we integrate over the small region like this one, so the inverse of square root T and the inverse of log T. So if you,
backwards?
yeah, it's backwards, yeah. So this quantity here will become log square T.
And that's the alpha T and beta T.
Yeah, this is the alpha T and this is the beta T.
But don't you, when you have like a square root log?
Square root.
No.
Oh, but that's inverse.
Yeah.
And then there's the same as in. So there's a square root on the log T. If I look at the beta T definition.
There is also minus here. And this is swapped, should be square root, should be this guy is on the left and this guy is on the right. So it's the lower T to the power of minus 1 over 2 is the lower limit of the integral.
So basically it's just alpha T and beta.
Yeah.
Okay, sure.
Yeah, but trust me, it's log square T, this thing here. Yeah, it's still crazy, this result. I mean, it's really not easy to understand it. But really the idea is that you should sample at this rate. And then this is for, you can integrate because we have uniformity and then take the limit. So using this intuition, Professor Lai derived this sampling condition for our problem. So he said, given to constant C gamma in 0, 1, we say that pi is a base uniformly fast convergence strategy if it satisfies this condition. So when we take the limit for capital T going to infinity, epsilon going to 0, but such that the epsilon squared still goes to infinity of this quantity, this limit is equal to 0. And this is the integral over the prior of this probability where this is for a fixed theta. This probability is the probability that we undersample, the probability that we sample at a rate smaller than this quantity. It means that pi, to be a uniformly fast convergence strategy, it needs to guarantee that you sample arm A at a value bigger than this. You cannot sample at a quantity that is smaller than this. It needs to be bigger because all of this is equal to 0. So this is really what this condition means. Here we see this log t epsilon squared as in the previous slide. We have the KL, and the KL is the KL between theta A, theta minus A star, plus some small quantity. This small quantity is the difference between theta A and theta minus A star. Yes, and then if we define theta A to be equal to theta minus A star minus epsilon, epsilon is indeed the gap. So we want to guarantee that as this gap is vanishingly small, this condition holds. So the algorithm should guarantee this condition. So
Wait, so can we look at the previous slide again?
yeah. Yeah, it's very similar. This should be t epsilon squared divided by the KL of theta comma theta plus epsilon.
Yeah.
And here we have theta A, theta minus A star plus some small quantity. And then we can also say that theta A is equal to theta minus A star minus epsilon. So here you can think of this KL as being equal to this quantity here at the bottom, 1 plus c squared epsilon squared. But c is very small, so it's essentially epsilon squared.
Okay. So what is the definition exactly of uniformly fast convergence strategy?
For the frequentist case? Or for this case?
For this case.
But this one.
Okay, so okay.
Yeah.
Did I interrupt you?
No, I was going to just say that, like, so I guess what we're sort of saying is that, like, a good strategy, which should satisfy
Yeah.
will satisfy this.
Yeah,
And therefore will, like,
a good strategy should sample arms at a rate
at least
bigger than this.
Yeah.
And because then we should also integrate over epsilon at some point. What will happen is that we should see this log square t appear.
Right, so that was the one. So intuition is if we first takes a limit and then into the expectation, it doesn't work because it will blow up as you showed. So, but one observation is we can do this this integral like in the previous slide, and that will make the integral not blow up. Basically.
Yeah. You first do the integral and then the limit.
Yeah, and then we based on that observation we have this
yeah. All right, so we were left here. Our gap, the integral over theta A minus theta minus A star. So as I said before, we consider theta A to be equal to theta minus A star minus a gap. And we want to look when epsilon is small, because that's the largest contribution to the regret. So we consider some open set calligraphic ET such that this set will converge to 0. So this is the set where epsilon belongs, and this set is converging to 0. So as in the limit, we are looking like for smaller gaps. So now, sorry, here the pose didn't work in Beamer. So let's start from the first integral. This is just a rewriting of this prior. So remember, h minus a is the prior without the prior on a that we write here. So we wrote the integral over theta k as two integrals over k minus 1, and then the integral over theta a. Okay. Then we said that theta a is equal to theta minus a star minus epsilon. So we have this integral here. It's a lower bound because we consider just some value of epsilon. And then we just do a change of variable. So remember, the gap can also be written as the difference of psi dot. So the mean value of the best arm minus the mean value of arm A times the number of times we selected arm A. And then here, this dHA can be written as the density. This is the density of capital HA times the epsilon after we did the change of variable.
Yeah.
Yeah.
Do we need to train this epsilon later? Oh.
Yeah. So I hope this is clear. Yeah. All right. We have this expression, and we can use the condition from the Bayes uniformly fast convergence strategy. So this is the quantity that appears in the assumption. Now we can just do Markov inequality on the complement. So when we do Markov inequality on the complement, what we get is that we can lower bound the number of times we selected arm A as 1 minus p theta. This p theta, it's this quantity here, that multiplies 1 minus gamma log t epsilon squared divided by the KL. And this holds for all theta. Secondly, we need now to lower bound the KL. But we know from the initial slide that the KL, it's an integral over psi second times a quadratic quantity. So we can upper bound everything by a constant, because psi second over an open bounded set is always upper bounded by some fixed quantity, which is C prime. And then the quadratic component is simply the contribution from psi and epsilon. So the idea is we lower bound this quantity by this using Markov inequality from the assumption. Then we again lower bound the KL using that the KL is upper bounded by this. Next, for small epsilon, under the assumption that the priors are like uniformly continuous, we can also say that HA theta minus A star minus epsilon is approximately HA theta minus A star. Also, the difference in the gap here can be lower bounded by a constant times epsilon by continuity. Psi dot is differentiable, it's continuous. So overall, when you combine all of this, you can say that the gap times the prior can be actually lower bounded by this quantity here.
Yeah.
So what's going on here? So this 1 minus gamma appears by the continuity of HA. So essentially we are saying for epsilon sufficiently small, we know that it will be 1 minus gamma away from HA theta minus A star. Then we are also using the fact that the KL is upper bounded by this quantity. So epsilon is upper bounding the KL divided by 1 plus C squared times epsilon. So that's why we also get this quantity here. So the gap is lower bounded by C epsilon. But epsilon is an upper bound of the KL divided by 1 plus C squared times epsilon. So when you combine all of these, you can actually say, oh, this quantity here, it's lower bounded by this. But then this KL cancels out with this KL when you combine also the lower bound on NA.
Right.
So overall, when you go from here and you apply all of this, you get 1 minus p theta times log t epsilon squared divided by epsilon. So log t epsilon squared divided by epsilon, 1 minus gamma HA theta minus A star. So this quantity here. Yeah. Do you want me to repeat it to go slower or?
That was fine.
Yeah.
You're lower bound this thing, you lower bound the expectation, you lower bound the other term, and the KL cancels.
Yeah.
Magically.
Yeah. So we are almost there. This is actually the quantity that we saw from the UCB slide. We still have this p theta that we will show that it tends to 0. Yeah, so this is the assumption that we had. But it's not exactly that we have here still. So we still need to show that this thing goes to 0 in some way. It's still not clear from this assumption how this will go to 0. Because here we have integral over theta k minus 1, but it's also here, but here we have also this integral that it's not here. So how does it really goes to 0? But we can look at this later. So for now, trust me that this thing goes to 0. So in the limit, when you take the limit now here, asymptotically, what we get is when we take the sum over actions also, because this was for a single action, to 1 minus gamma squared, sum over action, integral of the prior, integral over this small set epsilon of log t epsilon squared divided by epsilon. Under the assumption that this thing goes to 0. For now, let's focus on this. And if we have time, I can also explain to you why this goes to 0 later. So we have this integral, but I haven't really defined what is this set calligraphic E capital T. Lai show that this set needs to satisfy this condition. So the minimum value of this set, the infimum over this set should be this kind of 1 over square root T. A bit smaller than square root. 1 over 2 minus some small quantity. The upper limit of the integral shouldn't be polynomially decreasing, but should be in some sense slower, like logarithmic. So when we integrate this quantity, for example, in this region is like in the limit 0, and it's getting smaller and smaller. And when we take the limit, what we get is actually log squared t minus something that is log squared t. So now if you put this quantity here, and we let gamma tend to 0, and also t go to infinity, what we really get is that the regret in the limit divided by log squared t is lower bounded by this quantity here.
Yeah.
So, yeah.
Also check if the policy is uniformly.
Good question.
Not easy to
Not
check.
part of this presentation. No, but for example, in the paper, he derived a UCB method that shows that it's satisfies this.
I suppose in some way also satisfies. Oh, not clear.
Actually, I don't think anyone showed that Thompson sampling satisfies this. And I think at Sidaku, the Greek girl that was working on this,
All right.
she I think she has been working on this, trying to show that Thompson sampling satisfies this condition. She just shows also that UCB satisfies this, but yeah,
We don't know about Thompson sampling.
we don't know about Thompson sampling.
Okay, so what this shows is that these strategies that are uniform, blah, blah,
Yeah,
like the regret for these things will satisfy this bound.
yes.
The global.
So asymptotically, they need to satisfy this quantity. So what is this quantity? Because if I look at this, I have no clue. Like, I don't know about you.
No, it's just that.
Yeah. Do you have any suggestion?
Let's see.
It's not easy.
No, let's think. So is
I
that
can give you some intuition now, but I wanted
Intuition.
you to think about this.
It somehow looks like the entropy thing actually. The resource thing. The entropy because it has this HDH basically.
Just because we use H.
No, not that. That's a good one actually.
right?
All right.
That helps.
But it does look like entropy.
Yeah, I agree.
So the H inside is like
The density,
Right, no, but I mean, like, this is evaluated at like
the maximum.
the max over things that are not A.
Yeah.
It's kind of a strange thing. Okay, so what's the answer?
All right. So we will look at this
Congrats.
in a second. Congrats, first of all. There are some questions like what is the intuition showing that P converges to 0? Why do we need this in the limit? We will not answer all of this. Now we're going to the intuition, and if there is time, we can also discuss something else. But yeah,
So just one more. So like,
yeah,
so lie what in
it is
these works,
yeah.
what they showed, okay, this guy showed, was that I guess this uniform condition thing is about UCB, or what was it? Like, what
It
did
showed that UCB satisfied this.
Right. So I guess the logic of that paper was like UCB satisfies this kind of stuff. Now let's look at what's the lower bound for the regret for this.
Yeah.
And then blah blah, and you get this quantity, which now we're going to learn to understand.
But he also showed in another paper, like when we talk about the UCB, so in this slide here, so this one, so this is another paper. Here, he was studying the crossing boundary problem, the boundary crossing problem. So when a sum of random variables exceed a certain threshold in the Bayesian case. So this is without any actions. Just you observe a sequence of random variables and you want to understand when it exceeds a certain threshold. And they showed this condition independently from any sampling policy. So this condition gives you this rate here. So because of this is a strong indicator that probably then what this lower bound is probably a lower bound that holds in general for all techniques.
I guess my conclusion is that, let's say in frequent states, you show that, okay, no matter what you do, I guess if you have a lower, like,
Also for the frequency scale, you use a similar analysis for the lower bound.
Right.
First, you study the case where you have a sequence of random variables that you cannot control and study this boundary crossing problem when it exceeds a certain threshold to understand how many random variables do you need to like perceive an epsilon difference to do a detection. And then when you know what is this rate, you can apply it to problems where you can control, like multi-arm-bandy problems, MDPs, where you can take actions. Yeah. So here I provide some intuitions. All of this is like mine. Actually, in the paper, Light doesn't provide any intuition. So for me, the regret is characterized by the complexity of the priors. This integral really, it's an integral about the complexity of like the best value. A large K star implies a larger likelihood that A is close to optimality. So what it means is that if the density over theta star is very, very large, then it means that arm A can also be close to optimality. It can be close to theta minus A star, but theta minus A star is achieved by another arm. So if also arm A has high likelihood of having the same value, then the gap will be small. So it will be a more complex problem. And so the regret will be larger. So this is my first intuition. If HA theta minus A star is large, then it becomes harder to distinguish between A and the other best arm. And we can also try to simplify this. For example, we can assume the priors to be independent and equal. So we can assume the priors to be equal and IID. So when we have this condition, the H minus A is simply K minus 1 times the same prior. So when we look at the CDF of theta minus A star, it's simply equal to this probability that all the values of theta minus A are smaller than X. But this is just K minus 1 times the same CDF.
Yeah.
Because of independence. So using this fact, we can rewrite this integral as the integral over theta, a scalar, of the density H integrated over hk minus 1 theta. But now the differential of h to the power k minus 1, so you can think of the derivative of h to the power k minus 1 with respect to h theta to be simply k minus 1 h to the power k minus 2. So when you differentiate with respect to h, you get this quantity. And the h theta is also equal to the density times d theta. So we replace this dh to the power k minus 1 by this quantity. Dh is equal to a small h times d theta. So we get this nice quantity now, which maybe it's even unclearer than before. But actually, there is a connection to order statistics. So in order statistics, given a random vector theta, we say that the order statistics are this quantity here. So the assorted values of theta. So theta k and theta k minus 1 are the two best arms. Theta k is the best arm and theta k minus 1 is the second best arm. And we can actually show that the CDF or the PDF of the joint of the two best arms, it's equal to this. So when we take the limit here of this density as x tends to y, it's exactly this.
Right.
And this is also something that Lie didn't show. So we can actually draw a connection that this quantity here that we are integrating is the density of the top two best arms in the limit. So as the gap is vanishingly small. Another connection is that we can look at the probability that the top two order statistics are smaller than epsilon. So from the previous slide, we can actually write this as this integral here using this density. So using this density, we can just integrate in this way over theta and epsilon. And for epsilon small, this is just simply equal to k star, this thing here, times epsilon. So when we divide this by epsilon in the limit, we get exactly the quantity that we derived in the lower bound.
Right.
So the probability of the top two samples being smaller than epsilon divided by epsilon converges to k star. So this is the chance that the top two samples fall into a tiny interval.
Right. Yeah, that's interesting. Is there a way to derive, like from here, get some kind of lower argument without doing what he did for this specific case of like all the densities look the same? In a simpler sort of
Maybe.
calculating way.
Maybe, but this holds only if you have these independent priors.
Yeah,
It derived it in the general case.
Yeah.
So what he did was really masterclass, I think. All right, guys, this is over. You can chill now. We have some examples. Not too quickly. Yeah, just some examples of like what it looks in practice. What is the scaling of K star? So this quantity here. So I tried with with three priors: uniform over 0, 1, Gaussian prior, and Bernoulli. So what we saw in the first slides. We consider a multi-arm bandit problems with K arms and Gaussian rewards, and theta A is drawn from the priors. And this is how K star scales the number of arms. And I mean, the Bernoulli prior doesn't really make sense because the lower bound was not derived for a Bernoulli prior. It assumed uniform continuity of the prior, so it doesn't really, it's not representative. But for the uniform and the Gaussian, it's very interesting. We note like this sort of linear scaling. Also, the Gaussian is increasing, but very slowly. And I think it's interesting. And then here we have the slide from before. So when we try to compute the Bayesian lower bound using this technique, we get the orange curve. And the frequency just explodes.
Yeah.
So ideas, can we use the lower bound to design optimal methods? Probably. My intuition is that we need to solve some optimization problem. Like we need to solve an optimization problem where we try to optimize the number of times, the rate at which we sample arms. So this is the regret, subject to some condition on the KL between theta A and theta minus A star, something like what appeared in the assumption. I think something like this should work. So I don't know like what is the exact derivation, but probably should work. So conclusion, an extension is how to derive optimal algorithms based on the lower bound, try to maybe study for MDPs or best arm identification.
Yeah.
And that's it.
So,
Yeah, so my icons were some from my website. Since this will appear on YouTube, yeah.
Very good.
I don't know if you still have some willpower to check the proof of P theta going to 0 or just want to have.
Oh, that's it? Like, is it the next two slides? Or...
Yeah.
Okay. Yeah, very good.
Or is there any
one on
questions
the-
maybe so far from Spiros? Yeah.
They fell asleep.
No, no questions. But I think like I have to go through it, change the notation because all these eight thing stuff. Yeah, I got confused.
Bro, you think it's the entropy? Oh.
I will send the slides later.
Nice.
Perfect. Okay.
So we wanted to show that this double integral converges to 0, where this calligraphic E capital T is a sequence of open sets bounded such that it converges to 0. So yeah, we can rewrite this integral. So we can upper bound it by this quantity here. So we just upper bound this by the supremum over p theta. P theta is a probability, so it's always upper bounded by 1. But we upper bound it over epsilon that belongs to this set, the set of the integral. And we multiply by the Lebesgue measure of that set. So how big is this set? Okay, we can do this, but what we have is this condition. This is the assumption on the sampling rule. So what does this mean, actually? This limit means that for each value of delta, where delta is basically an upper bound on this integral, there exists a certain time, certain value alpha, certain k, such that this integral is smaller than delta whenever t epsilon belong to this set. So whenever t is bigger than t delta, epsilon is more than alpha delta, and t epsilon squared is bigger than k delta, then we have this quantity being smaller than delta. Now let's say we consider the set from before. So for this set, we know that for each value of alpha delta, there exists a t prime delta such that the inverse of log t will be smaller than alpha delta whenever t is bigger than t prime delta. At the same time, we also have this condition here that for each value of k delta, there exists a t delta second such that t gamma is bigger than k delta whenever t is bigger than t delta second. So this condition is related to this one. I replace the value of epsilons. So the epsilon are the two limits. So I replace the values of epsilon and with these two quantities, and it's possible to see that for each values of alpha of k, there exists some t prime and t second, such that the two conditions are satisfied, these two. So now we can set t delta star to be the maximum over all these capital T's, t prime, t second. So whenever t delta star is bigger than all these quantities, all these conditions are satisfied. So we have that actually gt epsilon is smaller than delta for all the epsilon in this set. So we have a uniform condition over this set because this quantity holds for all the epsilon in this set here, because we verified at the infimum and supremum of this set. So this condition is uniform over the set. Therefore, what we have really shown is that this quantity here, gt, is this integral. What we have really shown is that the limit of the integral is also equal to the limit of t that goes to infinity of sup over epsilon of this integral. Now, if you look at this quantity, this is the measure of the set calligraphic E capital T times the supremum of gt, the integral. We can lower bound this by the integral over this set. Gt, we can also remove the supremum. Gt becomes then an integral. Gt was defined here. It's this quantity here. So we can lower bound this by this double integral. But everything is bounded. We can swap the two integrals. And this is always positive. Everything is positive. But we just show that this goes to zero, this quantity here. This is also lower bounded by zero, so everything goes to zero. And this is exactly what we wanted to show, that this goes to zero. So this goes to zero, this is a bounded set, converges to zero. So when we take the limit of this quantity on the left, it goes to zero. The lower bound of this is also zero, so it must converge to zero. So that's why it converges to zero in the end. Yeah. So that's it, guys. I will stop the recording.